Artificial intelligence and machine learning are transforming various sectors, and mechanical engineering is no exception. These technologies are revolutionizing how engineers design, manufacture, and maintain mechanical systems. From self-driving cars to smart factories, AI and ML are driving unprecedented advancements. This essay will explore the real-world applications of AI and ML in mechanical engineering, highlighting their benefits and challenges. Human-machine interaction is a key area where AI is making significant strides. AI-powered interfaces are becoming increasingly intuitive, enabling engineers to interact with complex systems more effectively. For instance, voice commands and gesture recognition are simplifying tasks and improving user experience. Moreover, AI-driven simulations and virtual reality are transforming design processes, allowing engineers to visualize and optimize designs in immersive environments. However, the integration of AI in HMI also presents challenges. Ensuring the safety and reliability of AI-powered interfaces is paramount, as errors can have significant consequences. Additionally, addressing ethical considerations such as bias in decision-making algorithms is crucial for responsible AI deployment in mechanical engineering. Predictive maintenance is another groundbreaking application of AI and ML in mechanical engineering. By analyzing sensor data from machines, these technologies can predict potential failures before they occur. This proactive approach minimizes downtime, reduces maintenance costs, and enhances overall equipment effectiveness. For instance, in manufacturing plants, AI algorithms can monitor the health of critical equipment and alert technicians of impending failures. Consider a large industrial fan used in a power plant. Sensors on the fan collect data on vibration, temperature, and operating hours. An AI algorithm trained on historical data and failure patterns analyzes this real-time sensor data. The algorithm can detect subtle anomalies that indicate bearing wear or imbalance even before these issues become noticeable to human operators. This early warning allows for scheduled maintenance, preventing costly downtime and potential catastrophic failures. Fault detection is crucial for ensuring the safety and reliability of mechanical systems. AI and ML algorithms excel at detecting anomalies in sensor data, enabling rapid identification and diagnosis of faults. This capability is particularly valuable in complex systems where pinpointing the root cause of a failure can be challenging. In automotive engineering, for example, AI-powered systems can detect engine misfires or brake system malfunctions, enhancing vehicle safety. Dynamic system order reduction is a technique used to simplify complex mathematical models of mechanical systems. AI and ML algorithms can automate this process, making it faster and more efficient. This simplification facilitates analysis, control, and optimization of intricate systems, such as aircraft or robots, without compromising accuracy. By reducing the computational complexity, engineers can design more sophisticated control systems and optimize performance more effectively. Image-based part classification is another area where AI is transforming manufacturing processes. AI algorithms, particularly convolutional neural networks, excel at image recognition tasks. In manufacturing settings, CNNs can be trained to identify and classify parts based on images, automating quality control and sorting processes. This automation increases efficiency, reduces errors, and frees up human operators for more complex tasks. The future landscape. AI and ML are revolutionizing mechanical engineering. Reinforcement learning optimizes complex processes. It trains AI to learn optimal strategies. In manufacturing, it reduces waste and improves quality. AI enhances material inspection accuracy, detecting microscopic defects invisible to the naked eye. Essential for industries like aerospace and energy, AI optimizes control algorithms in real time, improving system efficiency and stability. For instance, in HVAC systems, AI optimizes temperature control, reducing energy consumption while maintaining comfort. The integration of AI and ML in mechanical engineering is revolutionizing the field, ushering in a new era of intelligent systems and processes. From predictive maintenance to fault detection and process optimization, AI is enhancing efficiency, reliability, and safety across various applications. As AI and ML technologies continue to advance, we can expect even more transformative applications in the future, further blurring the lines between human ingenuity and machine intelligence in mechanical engineering. In this bonus section, we'll explore an essential application of AI in mechanical engineering material inspection. Detecting defects and evaluating material properties with precision is critical for ensuring quality and safety. The process begins with data acquisition, which can include capturing images, ultrasound or X-ray scans of materials. This data is then pre-processed to reduce noise and enhance features, making it more suitable for analysis. Next, supervised learning algorithms classify the material quality. These algorithms are trained on labeled datasets to recognize patterns and anomalies, enabling the detection of defects such as cracks or voids in castings. For instance, in non-destructive testing (NDT), AI can analyze ultrasound scans to detect internal flaws without damaging the material. This not only enhances reliability but also optimizes the inspection process, saving time and resources. As AI continues to evolve, its role in material inspection will become even more sophisticated, contributing to higher standards of quality and safety in mechanical engineering. In this final segment, we're diving into another fascinating application of AI, the tuning of control algorithms. Optimizing control parameters is crucial for achieving desired system performance in various engineering fields. Traditionally, this process can be time-consuming and relies heavily on expert knowledge. However, AI is revolutionizing this space with its advanced capabilities. One prominent example is the real-time tuning of PID controllers using reinforcement learning. PID controllers, or proportional integral derivative controllers, are widely used in industrial control systems. By employing reinforcement learning, these controllers can adapt and optimize their parameters on the fly, ensuring optimal performance even in dynamic environments. Deep learning is also making waves in adaptive control, particularly in robotic systems. These AI-driven models can learn and adjust control strategies in real time, allowing robots to perform complex tasks with greater precision and efficiency. Let's consider an example tuning HVAC systems for energy efficiency and temperature stability. HVAC systems are essential for maintaining comfortable indoor environments. With AI, these systems can continuously monitor and adjust their parameters, optimizing energy usage while maintaining ideal temperature conditions. This not only reduces operational costs, but also contributes to environmental sustainability. As AI continues to advance, its applications in control algorithm tuning will expand, bringing unprecedented levels of efficiency and performance to various industries.